We are very honored to have Dr. Thomas Wiecki to address us all. Without further ado, Dr. Thomas Wiecki, please.
I think like this. Thank you so much. This on? Can anyone hear me okay? Great. Let's check this out. A second. So yeah, thank you so much for inviting me. This is the first time for me in Singapore. It's really great to be here and have such a great turnout. Thanks to the organizers. So as you know, I'm Thomas Wiecki from Quantopian. Someone stopped working. All right, sorry about that. So I'm currently the lead data scientist at Quantopian, where we are building the world's first crowdsourced hedge fund. And I'm going to be talking a little bit more about that, but the contents of the talk are going to be geared a little bit differently to a specific problem that we're having. I started working at Quantopian about 3 years ago while I was still in grad school studying cognitive neuroscience. And that's where I got exposed to Bayesian statistics and really saw that this has led to quite a paradigm shift in cognitive neuroscience, but also more theoretical fields like machine learning, where these methods have really been applied. So then, being a newcomer to quantitative finance, I sort of expected that those kind of tools were also being used by quantitative finance. But actually what I found is that the uptake has not been quite as much as in those other fields. So, I mean, the question is why, I guess. One is, well, maybe it's just not the right tool for the job, or people don't really know about it. And hopefully I can convince you that it is actually a very powerful tool and can provide a lot of value to quantitative finance modeling. I want to provide different kinds of motivations because I realize that probably not all of you are like hardcore into quantitative finance. And one of them is the data science motivation. Actually, can I get a show of hands who like here is from is like a quant or mainly interested in quantitative finance? Very few. And who is more considers himself a data scientist or interested in data in general, in modeling, that kind of stuff? Who's too shy to raise their hand? Okay. So ideally, when we model data, right, the way you think what should happen is, well, you have a specific problem, a specific data set with structure, you build your model around that, and then you turn to the problem of inference, of actually fitting that model, and then using the insights that you gain to like learn about your problem. However, in reality, often it works the reverse. The model is extremely constrained by what you are able to fit. And one example of that is the normality assumption. In quantitative finance, everyone knows that returns are not normally distributed, right? They have heavy tails, but still, a lot of cases, if you read a paper, they still say, well, we're going to assume it's normal. Why do they do that? Well, the reason is it's mathematically has very nice properties. So that's why you still find models that actually are not as realistic as they could be, just because those are the only ones that you can fit. And I think that's actually a terrible state of affairs. And one of the things that's wrong with statistics is that models should not be built for mathematical convenience, but to most accurately model the data that you have, right? And well, there are many pre-specified models in frequentist statistics, like a t-test or something, and those, however, have many assumptions baked into them, like, again, the normality assumption. And if you break them, it's very easy to shoot yourself in the foot and get wrong answers to your questions. Another way to look at this is by comparing it to machine learning, where, I don't know, you have a support vector machine, say, and those methods are much more flexible because they often do not depend on, they don't make strong assumptions about about the space of your data, right? They often infer that space and then fit some hyperplane through that. And that's fine, but often it's very difficult for these models to convey what they have learned. And I'm going to argue that probabilistic programming is actually sort of the best of both worlds here, and gives you a very flexible tool and allows you to really gain insight into your data. Said another way, much better, the purpose of computation is insight and not numbers. Second motivation is more quantitative finance. A lot of quantitative finance deals with risk, right? And you all know about systematic and unsystematic risk, like volatility, the tail risk, beta drawdown, those kind of things. And there's countless number of metrics to track all of that. However, there's this completely orthogonal source of risk that I think people are not often thinking about enough. And that's mundane things like program errors, and Knight Capital certainly experienced that. There is data issues, and at Quantopian we go through a lot of lengths to actually make it reduce the probability of you making those kind of errors. Today, though, I'm going to be talking more about model misspecification. Is actually, I don't know, are you violating the normality assumption, or also estimation uncertainty, and we'll be talking a lot about that. Very high-level overview of probabilistic programming. You can think of this as there's unknown causes, right, that we want to infer about, and we're going to model those as random variables, and we'll give a quick primer on what random variables are and an intuitive way to think about that. And you then write a programmatic story in code of how these unknown causes result in observable data. So it's a generative model. You think about, like, how was my data generated, right? So that's a forward model. And then you can invert that model using Bayes' formula and infer, given that data, what is the most likely state of affairs. And then connected to that, you write this model in computer code, which is extremely powerful. The other nice piece to that is that the inference process is completely automatic if things go well. There's a very general class of inference algorithms that I'll only briefly mention later, Markov chain Monte Carlo, that basically allow you to code up any model and then hit the inference button and not be concerned with, like, writing down formulas and, like, deriving sampling distributions and whatnot. And that is just, for me, the biggest selling point is that I don't have to, like, hire a mathematician or something to, like, figure out this extremely realistic model that I built and how I can fit that to data. I just, like, build it myself, and the inference is completely automatic. So I just can reiterate very, very quickly, change the model, see whether I break any assumptions. So it's a very liberating way of modeling. That, of course, comes at a cost, and that cost is increased computational demands. But with fast computers, better sampling algorithms, better software, that problem becomes less and less. And every day I take that trade-off between spending a few more hours estimating model and having a better model. Okay, so a few words about Quantopian. The first thing that we built was a web-based backtester for trading algorithms. And this is a screenshot of our IDE that runs in the web browser. So if you go to Quantopian, you can write Python code in the browser and write a trading algorithm that invests in the stock market. And then on cloud infrastructure, we stream data through that algorithm, and you make investments, and you see how your strategy would have done if you bought Apple in 2002 or something. In that case, you've done pretty well. The first question that people often ask when we tell them about this is, how much does it cost? And the answer is it's completely free. So you can just go to their website, and you don't even have to sign up to run your first algorithm. We have a great community of, like, pro quants and beginners that share ideas and discuss algorithms if you decide to share it. Then the second question we get is, like, if it's free, then this must just be an elaborate scheme to, like, get at users trading strategies, right? But actually, no. So our terms of use are extremely explicit that all of the intellectual property belongs to the person writing the algorithm. We don't look at the code. Actually, we take goes through great lengths of securing your code for like others, but also for ourselves. Yeah, so everything you do on there is completely private and belongs to you. And some users decide you can share it in our forums if you want to. You don't have to. And then the third question that we get, well, if it's not those first two things, how will you make money? And recently we announced that we will be using this, that we will be building a crowdsourced hedge fund. And the idea behind that is that we got this great quote from one of our investors: 15 uncorrelated return streams are the holy grail of investing. And there's just this really interesting property that you can combine many sort of mediocre return streams and get something that's really valuable, because you can really minimize volatility by combining uncorrelated return streams. So then the question becomes, well, how do you find many uncorrelated return streams? And crowdsourcing is, I think, one of the best ways to go about that. If you really want a very diverse set of ideas and just many eyes on that problem, then crowdsourcing is the way to go for that. Okay, so let's get a little bit more concrete and choose one specific toy. Well, it's not a toy problem, actually, it's a real problem, but we're going to narrow it down to a toy problem. And it's, well, how do we define these trading strategies, right? And the strategies that I'm going to use come from a contest that we launched in January. And you can enter it, and we evaluate we backtest and forward test the strategy and basically rank it on different criteria. And if you win, if you're the first in that month, then we invest $100,000 of our own money in your strategy and let it run for 6 months, and you keep 100% of the profits, and we eat the losses. So why do we do that? Well, for us, it's a really good way of sort of getting data of like various trading algorithms, only the returns, right? So we don't look at the code, as I said before, but we just like get their performance so that we can like start building up that tool of how do we actually pool all these strategies. And that's the problem that is my job and what I'm going to talk about today. So let's just select 2 strategies from that contest. Here I'm just plotting the daily returns histogram of both of these. And so we support live trading, and 2 brokers that we support is E-Trade and Interactive Brokers. Those strategies actually don't have anything to do with that, but we just needed a name that's easy to remember. So we're going to call them E-Trade and IB, the strategies. And those return distributions look like probably what you've all seen before. And we're going to, should we decide which one is better, right? So probably the first answer that many people would give is, well, we'll just look at the Sharpe ratio. It's a very common metric. It's not perfect, but it's used ubiquitously. You want high returns, and you want low volatility, so you divide one by the other, and a high Sharpe ratio is a good strategy. So we can obviously do that very easily on the returns. I just compute the mean, divide by the standard deviation. This is a normalization and annualization factor, and the IB strategy has a much higher interactive brokers, much higher Sharpe ratio, right? So obviously this one is much better. So if we have to pick one, we should just pick that one. However, it's not quite as easy, right? So what's missing from that number? Oh, uncertainty, right? So this is just a single number, but like, could that be 1.42? Could it be 0.5? Could it be -2? Like, we just don't know, right? It's just that one number, take it or not. And I also added a small wrinkle to this. We have 804 trading days for the E-Trade strategy and only 400 for the IB strategy. So intuitively, you say, well, with more data, we have more confidence, right? But it's not expressed in that number here. It's just a number. And I could have computed that over 5 trading days. Obviously, it would have been crazy large. But we just, we're just missing uncertainty quantification. And that's something that I'm going to say a lot more about. Okay, so to get at that uncertainty and lay some of the groundwork for probabilistic programming, we have to just build up some concepts of statistics, and probably most of you will know that, but I still want to be as inclusive as possible and try to give you just the intuition behind probability distributions and random variables and how to think about that. random variables represent our beliefs about an unknown state, and we use probability distributions to describe them, and we assign each possible state a probability. And critically, this is not a single number, right? So it's not only that one most likely state, but it's all states considered and all states associated with a probability. If you code, you know what a variable is, right? And a random variable is not that different. We can say, well, let's say we have a coin, and we want to reason about that coin. It can have heads or tails. So how should we write in code that can have two states, right? So certainly this is wrong, right? A variable can only have one value, and a random variable can have multiple. So that's the difference. Instead, we could say, well, the coin has a 50% probability of coming up heads or a 50% probability of coming up tails. And that's closer. It's not valid Python code, though. So that's where the statistics come in. And alternatively, you can just write that same thing as saying the coin is distributed as, so that's what that tilde means, as a Bernoulli distribution. And a Bernoulli distribution with P05 is exactly that. So it has 50% probability of coming up heads, 50% probability coming up tails. So a very simple distribution. And so coin in this framework is random variable. Bernoulli is the probability distribution describing it. And this is the distributed as sign. OK. That's the binary case. When we're dealing with returns, we can just extend that to the continuous case and say, OK, our returns now are distributed according to normal distribution. You all know that. With two parameters, mu, the mean, and sigma, the standard deviation. Easy. And the way to think about that is, well, here in blue, we have the actual random returns. And then in black on top, I drew a normal distribution that's supposed to describe it, right? So instead of dealing with the raw data, we're trying to find a distribution that describes it and then infer the parameters of that distribution. By the way, if you have any conceptual questions, feel free to ask throughout. OK, so then how do we estimate these two parameters? And everyone will know the answer to that. We just take the mean of the data, that's our mu, and we take the standard deviation of the data, and that's the sigma. Easy enough. And it's actually, statistically speaking, the correct thing to do. It's called the maximum likelihood estimate, and it's statistically guaranteed to give you the correct answer as n, the number of data points, goes to infinity. And quite some statisticians I know will be satisfied with that and say, OK, we're done here. Unfortunately, for us living in the real world, we don't have n of infinity most of the time, right? And that's where really, with limited data and noisy data, uncertainty about our parameters of the model is something that you should really care about. And the solution is, well, instead of just saying, well, we're going to set these as single numbers, we're going to turn them into random variables and look at them as distributions. How do we estimate them? It's not going to be the mean and the standard deviation, right? Luckily for us, Bayes' formula provides the answer. And what Bayes' formula does at the core is just shifting around beliefs, right? You have beliefs about the world. And thanks so much. You have beliefs about the world, and Bayes' formula requires you to define a prior belief without having seen any data whatsoever, right? What do you think the mean of this unseen trading algorithm is, right? And that's what trips up a lot of people is like, well, how can you reason about the world without having seen any data? But it's actually, firstly, an extremely powerful concept to be able to constrain your model. Secondly, also, often you do have a lot of information, right? I mean, will the mean returns be 100%? No, of course not. I know ahead of time that the probability is extremely low for that to happen. I know that it's going to be very close to 0. So I can incorporate that into my prior. And then I can use Bayes' formula to update that prior with the data and give me a new belief after having seen the data, what is called the posterior. And that's really the quantity that we're interested in, right? So we're looking for the posterior. And this will become more intuitive in a second. OK, so it's all about shifting around beliefs. OK, so now I'm going to be doing something over here. And so this is like an interactive applet that I will change. And over here you have the distribution for the mean. And what I'm going to do is I'm going to draw random samples, right, from a normal distribution centered around 0. So I know that the correct mu is 0. And then I'm going to see how I'm going to update my belief after having seen the data. And so far, I haven't seen any data yet. So down here, there will be like small ticks coming in where I start sampling more and more data. And I will update this in response to that. So as I said, there's no data yet. So this represents the prior information. I haven't seen anything. What do I believe about potential values of the mean? And I just chose this to be a normal distribution with a very wide standard deviation. We can argue about that, whether that's a good choice or not. But for illustrative purposes, it certainly does not matter. And it's just very wide. So it could be 20. The mean could be 20. It could be 40. I just don't know, right? So let's take a second and just intuit about what you think what will happen when I keep adding more and more data, right? So I'm going to keep adding data from a normal distribution centered around 0. So very intuitively, what should happen to like our uncertainty in this? So have you all formed a prediction? So when I move that lever, I'm going to add the first data point, and the second data point. So down here, you can see how the data starts trickling in. And over here, you see that basically how this changes over time. So on the x-axis is how many data points are added, and this is the width of the distribution. So as you can see, with more and more data, the distribution becomes narrower and narrower, right? And that represents my increased confidence in the mean, right? So with 9 data points, I'm very confident that the mean is going to be close to 0, right? Does that make sense? Do people like intuit that this is what's supposed to happen? Is like we get more data, we get more confident. And that's represented by this distribution shrinking around the true value. And just for fun, we can also compare that to the maximum likelihood estimate when we just use point estimates. And now we're not dealing with distributions, right? But we are dealing with single values. So each time I'm just computing the mean. And as I add like, I don't know, 600 data points, you can see what I said before, that this will converge to the correct value, right? We eventually do get to 0, right? There's 0, but it just takes a long time. Actually, even with 300 data points, we're off by quite a bit. So we're misestimating the mean without knowing it because we don't have a way to quantify uncertainty. And obviously, I'm not saying that Bayesian statistics is the only way to quantify uncertainty. There's like frequentist statistics and whatnot, and that's all fair. But I find that Bayesian statistics is a very intuitive way to think about this. And also, as I said before, because of probabilistic programming, we can do all of that automatically and basically design our own statistical models that way. And that's much harder to do with frequentist statistics. Actually, can you just click with the mouse, left mouse? Not on that, but anywhere else. Just there. Yeah, thank you. OK, so when we say that we're interested in the posterior, how do we get to that posterior? And right, that's that shape. And so we can evaluate Bayes' formula, but it turns out that actually Bayes' formula for even like slightly more complex models than like the simplest thing gets extremely messy. So you get like integrals over infinity, and yeah, it's basically intractable, right? And that, I think, held Bayesian statistics back for a long time because they were like, well, yeah, it's a great theoretical framework, but we just like can't solve it. Luckily, in the last couple of decades, and even more recently, a lot of work into sampling algorithms called Markov chain Monte Carlo have solved that problem by, instead of really getting this nice distribution, right, you can just approximate it by drawing samples from it. If we have a way to sample from this method that does not require evaluating it, right, then we can just draw many, many, many samples and do a histogram, and then we get something that looks just like it. Is that a question? Actually, a lot of mostly when I gave this talk before, I was like, well, and that's really the big problem. But actually, it turns out it's not a problem, right? It's actually amazing because that sampling algorithm works on like most models that you can dream up. So I don't even have to do any math. I don't have to like derive all those equations and solve those crazy integrals. I just run the sampler and I'm done. And there's this new class of samplers that work much better than what was there before called Hamiltonian Monte Carlo. And those are implemented in PyMC 3. So PyMC 3 is a Python package that I helped develop. And it's a probabilistic programming framework in Python. Allows for construction of probabilistic models using intuitive syntax in code. So you write Python code, and you just plug your random variables into each other. And it features these advanced MC samplers that, that work on really complex models and mostly automatic if things go well. And what's cool about it is it's written completely in Python, which would suggest that it's super slow. But actually, it's using Theano under the hood, which compiles that on the fly to C code, and then it's extremely fast. Because it's all Python, it's very easy to add new samplers or probability distributions. John Salvatierre is the main developer who like dreamed it up. And we're still in beta, mainly for lack of documentation. I use it in production. So we are currently writing the documentation, and it should be done any day now, and then we're going to release 3.0.
So how does it compare if you just bootstrap the sample actually? That's to get some results?
So you mean like instead of doing Bayesian statistics, just like do a bootstrap? Yeah. So you can do that, and it's definitely better than like not doing anything. I don't have time to go into that, but it has many like theoretical problems that come with that. Especially with small amounts of data, you can induce a lot of bias. So I mean, it's a valid approach. This, though, is theoretically, I'd argue, much more principled. OK, so that's it for the detour. Now let's get back to our problem, right? We wanted to compare two trading strategies, and we used the Sharpe ratio. So now we're going to build a Bayesian model of the Sharpe ratio and replace the mean and the standard deviation with random variables, and then infer those using MCMC. As I said before, with Bayesian statistics and probabilistic programming, you have to define priors, and these are the priors that I chose. And again, that's a choice that you make when modeling. And I just for the mean mu, I choose a normal distribution centered around 0. It's still very wide, right? So 0.2 would be 20% daily returns on average, right? That's unheard of. And but that's why it's weakly informative. Essentially, is I'm allowing for a lot of variability, and essentially let the data tell me what's going on. And we also have to define a prior for sigma, the standard deviation of the returns, right? The volatility. And here volatility can't be, standard deviation can be negative. So I'm defining a prior that does not allow for negative values. And I'm just going to choose a half normal, or the absolute value of the normal distribution. And that's what it looks like. OK, easy enough. So can you move that mouse pointer outside of the screen? Just like to the right, all the way to the right. Thank you. So this is what the model then looks like like when you write it as a statistician would. So mu is distributed according to a normal distribution. That's what I just showed you. This is our prior. Sigma is distributed according to a half normal distribution, the other prior that we have. And now we have to say, so this is like these unknown causes that I mentioned before, right, that I want to infer. And now I have to write this generative model of how do these unknown causes result in the data that I'm seeing. And I'm going to say that they result in normal data, that my data is normally distributed according to these two parameters, right? So that's how it connects this generative model. And then I can use the returns that I'm actually observing to invert this model and infer these two parameters that I'm interested in. And once I have the mean and the standard deviation, I can just compute the Sharpe ratio by dividing these two. And because this is a random variable and has uncertainty, and this is a random variable and has uncertainty, this will also be a random variable with uncertainty. So I'm getting a Bayesian Sharpe ratio, not just a single number, but a whole distribution in form of the posterior. And so because this is not, I can just compute those directly from those two distributions. So this is called a deterministic variable. And if you're more of the graphical type, this is the same thing, just in graphical terms. We have the mu as a prior, right? This is similar to the graphic before with the Bayes formula. Here we have our priors, here we have the data. Bayesian gives us, transforms those to the posterior. So how should we adjust our belief after having seen the data? And one thing that people easily get confused about, but what is very important to keep separate, is that those two things are completely separate, right? So there's the space of the parameters that I care about, mu and sigma, and then there's the data space. And those two things are completely separate. And here in this data, and we mostly care about this parameter space, right? So here is where the sampling will be done. Here is where I'm going to do the Bayesian updating. This over here, I'm not sampling, right? The data is fixed, right? This is just the input I'm going to use to infer those parameters, right? So just important to keep those separate. Okay, so next I'm going to show the model, but before that, just what the data looks like. And so these are just the daily returns that you looked at the very beginning. And this is what the model looks like in PyMC 3. So this is Python code. I don't know how many are familiar, but I find it pretty easy to read. So Python works with namespaces, so we first have to import the module PyMC 3, and I'm just going to import everything. And this essentially establishes a model context. So it's actually not important. It's a technicality, and it's boilerplate code, so every model will have that line in that. So, but essentially, it just ties everything down here to this model object. But here's where it gets really interesting. So when you remember from before, where we had this model description, we had mu, the mean return, was a normal distribution. So here I'm defining now my priors. And in PyMC 3, a normal distribution is just called a normal distribution. And the first parameter is the mean, is the name, right? So I just give that distribution and that random variable a name. And I'm going to say what the parameters of that prior are, right? And that's what I showed you before and what that looked like. So this sets up the priors, and now I have to say, well, I have these unknown causes. How do they relate? How do they generate the data? And as I said before, also, I'm going to assume that my returns are normally distributed, and that's separate, right? So again, this is like the observed data, and I could choose a different distribution here. These are not related. So I'm going to give it a name, and this is where I'm going to say, well, the data are distributed according to this random variable mean return, and the standard deviation I want to infer is from the volatility. And here, this observed keyword is what turns this into something different, namely the likelihood of how these parameters can be inferred. And this is where I pass in that vector of returns, right? So this is what connects the unknown causes to the data. And once I have this set up, I can just divide one by the other, and this again is my annualization factor, and that's what will give me the Sharpe ratio, right? Okay, so now, up until now, nothing has really happened, but now I'm going to run the sampler, and nuts is one of those magical new samplers that works so much better. And I call the sample function, and it gives me a trace back, which is the samples from the posterior that I'm interested in. So now I can look at that posterior to get at what my posterior looks like and my uncertainties. And I ran that model now on both strategies, and we can compare those two and the different parameters that are inferred. So for example, I can look at the mean returns, right? So before, we could just take the mean, right? But again, that was just a single number. Now we're dealing with distributions, right? We think about what's the probability that the mean return is 0? So that gives me an actual number. What's the probability that it's 0.5%? And so again, it's not a single number, but just every possible value gets a probability associated to it. And also the other nice thing to note is, if you remember from the beginning, one strategy, the IB strategy, had 800 days, and the E-trade strategy had only 400 days. And we said that our uncertainty increases, our certainty increases with more data, and that should be reflected in the posterior by being more certain about what likely values are, or what the likely values are. And as you can see, this distribution is much narrower, which reflects that text. So that is a very rigorous way to reason about uncertainties. You can also look at the posterior for volatility. The E-trait seems to have much higher standard deviation, much higher volatility, and we can compare them in terms of the Bayesian Sharpe ratio. And again, we see, as we did before, the IB strategy does seem better, but there's still a lot of overlap, right? So now things don't look quite as clear-cut anymore, where like one was 1.4, the other one was 0.6. So now we have, we see that we still have a lot of uncertainty in that Sharpe ratio. So we can't really decide whether it's, I don't know, 1.5. It could also be 0 with like non-negligible probability. And now we have that posterior, we can inquire it and ask statistically meaningful questions. Like, for example, what is the probability that the Sharpe ratio of the IB strategy is larger than 0? And it's very easy to just like look at the posterior. You don't have to understand this, but we get back a probability of 96.4%, right? And that gives you exactly what they're looking for, like the risk of investing in that strategy, or the risk that this Sharpe ratio is actually negative, would be 3.5%. And we can also compare the two and say, what's the probability that the Sharpe ratio of the IB strategy is larger than the E-trait? And it's 80%. So not really where we would be confident saying, well, this one is definitely better than the other, right? I'm going to skip this. So far, we've seen that we can use Bayesian statistics to very flexibly create models and reformulate a lot of the risk metrics used in quantitative finance. We can place priors to inform the model, and the IB strategy seems better, right? So seems like we're good to go. And I want to remind you just that the model that we built still gives us the same answer as before, right? So here I'm plotting the same posterior as before, but now there's these two lines where the Sharpe ratio that are computed manually before, right? Just that single number from the beginning is basically where this says it's most likely as well. So those two agree. We just added uncertainty to this, which is cool, but the question is this a good model or not? And how am I doing on time, by the way? Okay. So here I'm plotting the raw data, the returns from before, and the normal distribution that is fit by the model. And this is not just a single line, because we don't ever deal with only single numbers, but we have uncertainty in here, and that's reflected by the width of that distribution. But certainly what you see is this is a terrible model, right? This doesn't look at all like the returns over here, right? This is much more peaked, and there seem to be all these heavy tails, which you'd expect. So now instead, we can just change our likelihood and say, instead of the normal distribution, let's choose one with heavy tails, like the t-distribution. And I don't have to do anything now, but just like change a single line of code in my model and say, well, instead of normal, it's now t-distributed. And still, the inference will just like happily sample from this other model, so I don't have to like derive any equations or anything like that, which is kind of cool. So yeah, I guess this should be on another slide, but you can see in yellow now, this fits the distribution much better. And we can compare now, for a single strategy, the different answers we get from the normal distribution model, from the model that assumes returns to be normally distributed, and from the model that assumes returns to be t-distributed. And for example, the mean now actually is quite different, right? So we think that the mean, we're more confident that the mean is actually lower than we thought before. We can also look at the Sharpe ratio, and this is really striking, right? This is the same data, just with a different assumption of the distribution of the data, and the answer we get is completely different, right? What looked before like a pretty good strategy now looks really terrible, and we're pretty certain that the Sharpe ratio is much closer to 0. So why is that the case? The answer is it's all in the tails. The t-distribution is much more robust because of its heavy tails. So here, this is now data that I generated. So I sampled from a normal distribution, and then I added a single outlier over here. And I plot the best fitting normal and the best fitting t-distribution. And as you can see, that normal distribution is extremely influenced by that one outlier over here. And that's because if the red line would be looking like this data point over here would have extremely low probability, and that would mess up your model fit. So just a single outlier can completely screw up your estimation. And the t-distribution is not phased by that, because even with this shape, this data point is much more likely given the heavy tails. OK, I'm going to skip this. And now we can compare those two strategies again. And what's interesting is that now actually it has shifted, right? The E-trade strategy now looks actually much more appealing than the IB strategy. So before, on the normality assumption, those were flipped, right? So this is kind of striking that just improving our model even a bit gives us completely different answers. And also note that the answer from before with the normality assumption is the answer we also got from the Sharpe ratio that we just computed manually. So something as benign as just taking the mean, right, seems totally harmless. But actually, there's sort of an implicit normality assumption in there, because the mean is an extremely bad estimate. You should basically never take the mean, because it's extremely easily influenced by outliers. And if you have heavy tails, there will be many outliers, and the mean will be that much more noisy. So if you don't care about anything, just like take away that you should never take the mean and just take the median. And I can also compare now the probability of these two. It's cut off, but the probability is, I don't know, close to 95% that actually E-trade is the better strategy. OK. So to wrap up, I hope that I showed you just a little bit that probabilistic programming allows us to construct complex models. What I dealt with was just the tip of the iceberg, actually. You can like build much more complex models, and these samplers are still able to infer that. And that's just extremely liberating, that I can really not keep thinking about like, oh, but how will I ever fit that model? I just like think about how's my data structured? How can I build a model that gives me the answer that I'm interested in? And there's many added benefits, like uncertainty quantification. We can include prior information and all of that, and measure these orthogonal sources of risk, like I said at the beginning. And PyMC 3 puts those advanced samplers at your fingertips, so you don't actually have to implement anything by your own. You can really only focus on writing your model in code, and that's that. I'm going to upload these slides so that you can look at these links if you're interested in following up more. Definitely check out Quantopian, develop a trading strategy that hopefully does well. And yeah, these are just some more things, and follow me on Twitter if you're interested. But yeah, thank you so much for your attention for such a long time. Happy to take questions if we have time. Please.
If you changed your model from normal to T, what happens if you choose another heavy tail distribution? Does it change pretty much, or is it quite robust no matter which?
So without having tried it, I can't say. Yeah. But my intuition would be that that should not matter much. So in that case, the problem really was the outliers, and that's addressed by using heavy tail distribution. Or, well, it's not outliers, right? I mean, that actually happened. Like, it's just heavy tail data. Well, actually, so one thing is, if you had a keen eye, you'd seen that that distribution, one return distribution was negatively skewed. So it's not symmetrical, but actually, and that's also very common. And I did not account for that. And that actually might change. So let me revert my answer and say, it might, and my next iteration of the model would include the skew, the parameter for the skew. But it definitely does raise the question of like, yeah, when do you know when your model is good enough? And there's many ways of like checking the model. Like you can generate data from the model and compare that to your actual data and see how good the fit was. Any more?
I have one more then. But you have to choose one model. You cannot be like assumptionless.
So the question is, well, how do I know if I have the right model and that I have to choose one model at the end of the day? And that's true. And model building is hard work, right? So there are, though, many ways to compare different models. So you can look at like which model generates data that is more in line with the data that I've seen, which one has, and there's many measures to like compare, like, well, this model is very complex, so of course it'll fit the data better. So it penalizes model complexity, and so you have tools to like compare different models, and then hopefully that will tell you which model is the best model. Of course, you can only try a finite number of models, and the correct one is never going to be under those. But yeah, that's like where it gets sort of philosophical, in where you do need answers at some point, right? So you just have to make do with what you have. But at the very least, here this gives you the freedom to actually compare those different models, right? Like if you're just using a t-test, then I don't know, like if you're lucky, then someone designed that other t-test, but like I don't know, I couldn't derive that. So yeah, here you actually can build all these different models and compare them.
One way, maybe we could test how good the model is. Maybe do an auto sample test. So
Oh yeah.
Is there anything, any code or any scripts that's available for that?
Yes, so out of sample testing is a good way to go about that, and you can do exactly that. So you fit the model on like a subset of the data, and then you generate data again, and then you can compare to the out of sample data, or you can see like what's the likelihood of having observed this out of sample data given my model. So yeah, that exists. There is also some research, though, that shows that you're often better off with using all of your data to get like the most informative answer, and then using those model comparison methods that sort of devise that.
If my model have depends some number of factors, can this tool tell me which sector is most sensitive? So every time I feed him, I tell him, okay, these are the factors that have occurred, and then this is the result. Would he be able to tell me give me some insight as to which factor are more sensitive?
So is your question that when you have multiple parameters, say, and it tells you which parameters really matter and which of those are more nuisance parameters? Yes. So intuitively, actually, if you there's different ways, but one easy way to think about this is if you have a parameter that does not matter, right? Then it will not you will not be able to learn about it, and essentially your posterior will look exactly like the prior, because none of the data actually informs that parameter. So you can look at how well were you able to inform that parameter, infer that parameter, and that's one way to look at that. There's other ways to like do a sensitivity analysis post hoc or like the posterior. So yeah, that's possible. I like the German soccer shirt. That's very nice. Well, okay, then I'll be around later for questions and everything. I really want to thank you all for coming out and checking this out, and definitely be in touch. Thanks.
Thank you.